In this video, I'm going to solve the following problems if possible using Lenz's law. Lenz's law says the following. The direction of electric current which is induced in a conductor by a changing magnetic flux will be such that the induced magnetic flux created by the induced current opposes any change in the original magnetic flux. That's a lot to take in, and let's go ahead and do an example to explain what it means. First off, part of Lenz's law is having a current. And we actually can't do it unless we have a complete loop. So it won't work for question A. But for question B, we can use Lenz's law. The steps are as follows. First, determine the direction of the original magnetic field or flux. Clearly, in this loop here, the magnetic field is directed into the page. Now, this is an existing or original magnetic field, and it is directed into the page. That's step one. Next, we want to look at the situation and determine whether the original flux will be increasing or decreasing with time. Since the area of this shape is getting smaller, the existing magnetic flux directed into the page would be decreasing if that bar were to proceed to the left. Now that we have that information, we can now determine the direction of the induced current in this loop. But it has to follow Lenz's law, which says that the induced current will create an induced magnetic flux that will oppose any change in the original magnetic flux. So we have to create a magnetic flux which will supplement the decrease in the original magnetic flux. You have to figure out what direction of current would create this. So what's needed here is going to be more x's into the page to compensate for the loss of x's when that bar moves to the left. And so we can label these new x's as B induced, it's called. And it creates a magnetic flux, which is, again, induced. But how is this supplementary magnetic field and flux created? It's created by a current in the wire. So we have to think about what kind of current in the wire would result in a magnetic field pointing into the page. For that, we want to go back to our right-hand rule of grabbing onto the wire where the fingers are the magnetic field. This time, the fingers need to represent the induced magnetic field. So we want our fingers to wrap around the wire such that the fingers end up pointing into the middle of the loop. And then when we're using our right hand, this would cause the thumb to point to the left. And so that is a way that we can tell what the direction of the induced current is going to be. Apparently, according to the right-hand rule here, the induced current is directed clockwise. Now, the results that we get with this analysis should match the results we got with the other approach that I had taken in my previous video. In my previous video, I used this right-hand rule here to see what kind of forces would be created on the particles in that moving wire. And I determined that positive charge would feel a force in the downward direction, and that would cause a clockwise current. So this is two totally different ways of analyzing the situation, but we want them to agree on the direction of current. And in this case, they do. Okay, when it comes to question C here, there is no magnetic flux at the beginning, and there's going to be no change in the magnetic flux, so there won't be any current in that case. But we can use it in question D. Try the steps for yourself. Think about which direction the magnetic field and flux are at the beginning. Then think about how that magnetic flux will be changing with time. Will it be increasing or decreasing, and in which direction? Then we want to create a current which will oppose the change in flux through that loop. Take a moment and try it for yourself and see if you can guess the direction of induced current here. Okay, so for step 1, we see that the existing B field is directed out of the page. And the flux is, of course, out of the page as well. But how will the flux be changing? Will it be increasing in magnitude or decreasing? Well, the magnetic field is going to remain constant, but the area of the shape is increasing. The magnetic flux out of the page would be increasing. And according to Lenz's law, we have to have an induced field and an induced flux that will oppose this change. In my last example here, the x's had to be supplemented because the magnetic flux into the page was decreasing. But here, our magnetic flux out of the page is increasing. So we don't want to supplement it with more dots. That would make the situation even worse. That would make the magnetic flux out of the page even stronger. So instead, we want to combat it with a magnetic field of our own that opposes it. And what kind of current can create X's in this situation? Would it be a counterclockwise or clockwise current? Well, as you can see above here, a clockwise current will create a magnetic field that's directed into the page. So once again, we're going to need clockwise current in this loop in order to preserve the original magnetic flux through the loop. And that's what Lenz's law says. It says that the charges in a conducting loop will try to preserve the magnetic flux through the loop. In E, we see that the magnetic field is constant, but the area is not changing, and the angle between the field and the area is not changing. So there's actually no change in flux in this situation. This tells us there won't be an induced current in this situation, and that matches with what we had found in the previous video. In this situation here, we see that the area is changing, but the flux through the loop is not. We still have the same amount of field and the same area that that field affects. So even if the area of the entire loop changes, that doesn't change the flux through that middle. So since it is constant, there won't be an induced current in this situation.